Hi, everyone. Hi, Natalia.
Sounds, is it somehow sounds to you okay?
I hear you.
No more.
Here now.
Okay. So, hello, Rob. How are you?
Hiya.
How is your
Hi.
vacation?
It's been good. Bit interrupted by too much work.
So
Sorry,
you have no
sorry,
vacation,
Rob.
honest. Okay. Okay, we are waiting.
Harsha, could you try to speak? Because I want to test if all people can speak.
Hi. Yep. I'm okay.
Okay. Okay. Hi, Harsha. Thank you.
Thank you.
And I think that, Rob, you can share the screen only for tested.
Okay, let me do that. Present. Then I have to work out how I'm fighting a single screen, of course. So I need to work out how to juggle all these things. Yeah,
I can share my screen if you prefer.
No. Okay, let's try that.
Okay, perfect. Great. Hi, Diego.
Hello.
Can you hear me? Okay.
Hi, Diego.
Okay.
Yes, I can hear you.
Only testing that I can hear you perfectly. So I think that we can start the webinar. Thank you all to be here. Today we are exploring CityRDF, how this new technology can help to explore different data formats and combine all of them. Yes, we are very happy to have this webinar and show you the new advantage of the CityRDF. I want to present Rob. This is my colleague from OGC. He's have a long experience in semantic web and developer. He will present the webinar. Explore all the possibilities that this RDF have from the different perspective. So thank you, Rob.
Okay, thank you, Micah. I'll dive straight in. I won't say a lot because we have 4 presenters who've been doing lots of the interesting work we want to share. I just wanted to provide a quick overview of the sort of the context of what we're doing and why, and how it fits in to the broader OGC process of generating reusable standards. So I will go into a little bit more detail about what each presenter will cover, and then they will take it away fairly shortly. So just the casts here is myself. That's before I had a beard. Diego, Nataliya, Arkadiusz, Carl, we still don't have a picture for, sorry about that, and Alejandro, who sits behind the scenes and supports a lot of the tooling and automation we'll rely on to go through publication processes. So the first thing is just to put this concept of CityRDF into context. So first of all, let's just understand what we mean by RDF. RDF, the Resource Descriptor Framework, is a technology that's been around for a very, very long time, and it's been used in this sort of concept of the semantic web, which you may or may not have any experience in. It doesn't really matter. And this concept of linked data, which is a bit more important, which is the ability to link from one piece of data to another related piece of data, which dramatically increases the interoperability of information if it's possible to do that. The idea behind RDF is that it's a graph, it's a flexible data representation that is basically made a whole bunch of graph edges, 2 nodes with a relationship, what we call a triple, the subject, a predicate, or an object. And with that, we can really model anything we like. The RDF technology has a query language which allows us to do the funky things which are valuable, like arbitrarily walk through recursive structures and nesting, stuff which SQL struggles with when you have to manually join all the tables together. Sparkle allows us just to follow the path, but otherwise it looks quite similar to Sparkle. There's a range of implications about this, and one of them is you may not need to know the data structure in advance. That said, there's a lot of value in knowing the data structure in advance, because then you can create reusable queries and APIs and so forth. And that's where CityRDF comes in. For describing city data, what would those data structures look like in the graph? Once you have an RDF representation, which is, we'll talk about in a second, is characterized by having these unique web addresses for every node, there's a range of other technologies which can be brought together. One is OWL, which allows us to have a range of reasoning capabilities on top of it. And then there's other ontologies such as SCOS, the Simple Knowledge Organization System, which is a framework for creating definitions for things and how they relate to each other. And then a range of other things like DCAT, the data cataloging methodology. So one of the reasons for having a RDF representation of something like CityGML is we can do reasoning over it, which Arkadiusz will definitely show in more depth, and actually all the partners will. And GCAT, we can look at how we document these kinds of data sets. But the big advantage of a graph is you can connect things to it. You can enrich the data without changing it. You don't have to break your existing expectations of table structures or schemas. You can add more information to it as you go. And it's used in a range of environments, and it's increasingly being used. And I think that's something which is one of the drivers here. In particular, there's a lot of interoperability work happening in the European context where this move towards RDF is being driven, data spaces and so forth. So in a nutshell, RDF means that every concept has a URI identifier. That's a web address that is unambiguous and can potentially be followed or dereferenced to get more information. Once you have that, you can layer on more information about it. You can basically make statements about that concept. For example, how to map it to another concept, or where it came from, or what other attributes that you might want to connect to that. For example, if you have a building and you want to add some information about the appearance, or you want to add some information about the status of its building permit, you can connect it very easily without changing anything. So it's a very extensible model if you handle it in a scalable way. Of course, with a graph, it could become a mess very quickly, but the role of standardization in this context is to constrain the shape of the graph so that it doesn't all become a mess. And we'll walk through where we're up to with the CityGML representations. So just to note, the UML, which is regularly used and is used for the CityGML conceptual model, it's designed for human readability. Even though there is an underlying database behind it, it's not that easy to build and share and reference individual pieces of that. XML is another technology, and CityGML is the XML expression of that UML model, is not easily extended. And we'll go into some detail. Nataliya in particular will walk through the way we have to navigate the implications of XML versus RDF in terms of an easily extendable model. And it's very hard to make sort of logical references to create rules and so forth about what is supposed to happen with the content inside that data in those two technologies. You tend to get UML and that's it. Or you have XML, that's it. Where RDF itself has a range of different technologies that work together that can provide more power for your end implementation. And as we shall see, it doesn't really stop us using something like JSON. So if you think about how this can be done, here's a quick example where we take a model schema in JSON, for example. I could use XML, but it's messier and harder to read. But the big advantage of JSON is there's already a technology which allows us to map elements of a JSON to URIs, which is called JSON-LD. And if you do that, we can generate the RDF using standard tools, standard libraries, etc. So the pathway for moving from CityGML to RDF is dramatically eased if we have a JSON representation of CityGML. So given that there's increasing moves towards JSON representations to support OGC APIs, now is the time to think about the RDF, because anybody who's expert in JSON-LD will see there's a couple of little errors or issues in what I've done. It's actually very important to develop the JSON schema with the RDF target in mind, because that way this process can be done seamlessly and smoothly and simply. If you do it the other way around, then it becomes much messier. So we won't go into a lot of detail of that process right now, but to bear in mind, the context is that we're expecting CityGML to be expressed in multiple flavors, JSON and RDF, and there is a co-development methodology which is going to be much better if we do it that way than if we do separated efforts. So moving away from how we do it to who we do it, we can sort of invoke the FAIR principles. And the point about FAIR is for it to be reusable, it has to be stable. Someone has to make a decision to use it. So before you can reach the R part of FAIR, someone has to own this. We have to have governance, and that's where the who matters. So this webinar is going to provide a quick overview of where we're up to in the technical, the how, and it's really designed to facilitate the discussion around who is going to manage this moving forward. And can people please mute, because I'm getting a bit of feedback. And so in this particular project, we're going to look at a project called Accord and look at how this might move towards OGC and W3C publication of an option, and then its downstream use for projects like Check, which is I shall describe in a moment. So this is just a quick overview. The top layer there is the Accord project, which is about the logical rules for describing the semantics of regulatory compliance in the built environment, the construction center. And the bottom line there is the Check project, which is about implementing permitting processes based on profiles of those models, and actually testing to make sure that the information that you need to run those rules is present, and doing any transformations. So Accord and Check are two projects which have been working together to exploit various information models, including CityGML, including BIM models, including things like inspired land use models. The same process appears. However, one of the things we need is to have a version of CityGML which we can reference, and hence the drive for CityRDF. There's a bunch of different use cases inside the Accord project in Estonia, Finland, UK, and Spain. I shall leave it to the other team who are more actively involved to explain these as required. But just to give you a sense that there is some drivers and some testing behind the process, and it's not a purely academic exercise. So the real question is, how do we transition from this project initiation to a canonical published CityGML RDF standard? And we're aware that not everybody is fully aware of all the technical issues, which is why we're running this seminar to provide, to open the hood and to provide an opportunity to understand how this relates and what the technologies are. And we have a lot of experts on board to answer questions. And the other thing I wanted to put in a very sort of long-term vision is that we're currently looking at OpenAPI 4.0 is likely to include semantic annotation capabilities. So we potentially need to understand in our short term what our best practices are, and then we can feed it into things like that. So just in case anybody's interested in that sort of long-term strategic thinking and how this relates. So I'll just hand over now to the various expert presenters. So Diego will explain in much more detail how RDF can be exploited and some of the initial work with CityGML to RDF conversions he presented at Huntsville, if I remember correctly, about a year ago. Natalie will then look at how we have sort of taken that work up and look to progress it a bit further, and a couple of issues in there. Then Carl's got some interesting stuff about the advantage of having this model and what can be done with it. And I really want to highlight his sort of last thought, which is around the necessity to have simplified views of some of these standards that are ready to use in applications. And finally, Arkadiusz will go into a bit more detail about how Accord will use the model. So with no further ado, I shall hand it over to Diego.
Perfect. Thank you very much. Let's see. Let me just share my screen. Normally, everyone can see the presentation?
Not yet.
No,
Not yet.
No.
Let me try again. How about now?
Nothing.
Try again, Diego, because now you are a presenter as well.
Okay. If it's not working, it should be now.
Yes, it's coming up now. I think.
Perfect.
Yeah.
Yeah.
Perfect.
Okay, so thank you for that introduction. So my name is Diego Vinasco-Alvarez. I've been working here at the LYRIS Laboratory for about 5 years now, and I'll be presenting a lot of our work in transforming the CityGML standard towards an RDF OWL representation, data and how it can be represented using this kind of representation, and a couple examples that we've produced using versioned urban data. So first, a bit of context into our research and our methodology. From the beginning, we wanted to base our approach on standards in order to make sure that everything that we propose is highly interoperable with not only other research, but also industry that might be interested in our approaches. And for this, we chose to do a model-driven integration approach, where we not only transform the data that we'd like to integrate, but we also base this transformation off of the underlying data models that structure the semantics of this data. And so today I'll be presenting how we use this kind of an approach to integrate different data from multiple sources. This data can be very heterogeneous, and not only does it have spatial components, it also has temporal components, as we would like to visualize not only the semantics of the city, but how the city itself can evolve over time. I'll give a couple examples for how we can use logical rules to validate and infer new data using the inferencing that Rob mentioned earlier. And then, yes, like I mentioned, a couple experimentations that we perform using visualization and navigation to exemplify how this data can be visualized and navigated. Excuse me. So a bit of a state of the art in the approaches that we used. I won't be mentioning everything that's important to the research that we have produced, but I'll be going over 3 main approaches that we based our transformations off of. The first is ISO 19150, which is a standard that allows us to transform geospatial compliant UML models with the 191 ISO series of standards towards many different things, but in specific OWL ontologies. This standard gets the transformation from UML to OWL mostly completed. There are a couple limitations to note, but it does a great job of creating an initial ontology. And I'll talk a little bit about some cleanup steps that we had to perform after this initial transformation. Another thing that's important to take into consideration is alignment between ontologies. When I talk about an ontology, this is effectively an OWL graph, but it is formed with it's described with a formal language. And an alignment allows us to make links or correspondences between the different concepts and data instances of these ontologies. This allows us to reuse existing ontologies in the semantic web after we've transformed our data models and our data. And an approach that uses this alignment is creating networks of ontologies, where we can take, instead of focusing on one massive ontology, we can break it up into smaller local ontologies, and then align all of those ontologies with each other. And if we do this correctly, we can have these more domain-specific ontologies reuse the same vocabulary of a more domain-agnostic ontology. And this is the approach that we used when aligning. So here is an overview of our integration workflow. It's divided up into 3 main steps. First, a transformation from UML to OWL. Then we can use the ontology that we create from this transformation to guide the transformation of instances, data instances, towards a representation that is conformant to the ontology. And then after that, we'll align this ontology with existing OWL standards. In practice, we used CityGML's 3.0 conceptual model. it had a lot of the semantics and structures that we needed for representing geometry, for representing urban semantics, and for representing versions of city data. For transforming the data, technically we used a tool called shape change, where you can pass in transformation mapping rules, and it'll automatically transform your UML model to many different shapes, but obviously we chose OWL for our target. I'll be referring to the results of this transformation as City OWL informally. It's not like an official name or anything. And one thing to note is that all of the tools that we produced to manage these transformations, we stored in a GitHub repository called UDgraph. So when you do the initial shape change transformation, there is a bit of cleanup in order to make sure that the ontology rests logically consistent after transformation. I'll talk a little bit about this later. Those are found in UDgraph. And then the transformation of data that's conformant to the CityGML standard towards an ontology that is conformant to the, data instances that are conformant to the generated CityOwl ontology are done also in UDgraph. Our alignments we store also in a separate data set, allowing people who want to reuse this data to pick and choose which alignments they'd like to incorporate. And then we chose to align the generated CityOwl with GeoSparkle for representing geospatial semantics, and OWL time for representing time-dependent components of city data. So what does the transformation look like? So CityGML is divided up into a series of modules. Some of them are thematic modules that are much more domain specific. For example, modules representing building semantics, bridges, tunnels, transportation networks. And then there are more domain agnostic modules for representing, for example, how these real world entities could be versioned, for representing IoT sensor data with a dynamizer module, things like that. Following the ISO 19150 transformation mappings, all of these individual modules are transformed into their own modular ontology. And when we're aligning with more domain agnostic ontologies like GeoSparkle or like OWL time, we only have to make alignments between the very abstract core module of CityGML. And so initially we proposed two transformations of CityGML towards OWL. One we're calling more of like an open world interpretation of the CityGML model. It is much less constrained following, it's very similar to how the CityJSON standard generates their schema. There's much less constraints imposed in the schema itself, but that doesn't prevent you from creating data that is 100% conformant to CityGML. And this has the advantage of being much more lightweight as an ontology. And then we also proposed a much more constrained ontology that has all of the constraints from the original UML model. This is very useful for when you want to validate your ontological data that you want to be conformant with CityOwl, because you can then use inferencing, and I'll talk about this a little bit later, on these constraints to make sure that your data has the right structure and is following the logical rules imposed by the ontology. Now, for representing 3D geometry using this generated CityOwl, there are many different approaches in the state of the art. You could store your geometry directly in RDF. You could use standards like GeoJSON LD. There are standards like GeoSparkle, STSparkle, STRDF that allow you to store GML literals, GML geometry as literal strings inside of your ontology, and then you can query those natively with GeoSparkle. In the end, we chose an approach where we keep all of our semantics in the ontology, and then geometry we reference by linking to whatever geospatial representation we would like to visualize. We had an experimentation where we transformed IFC and CityGML data to 3D tiles, and then we simply linked our ontological data representing these real-world entities towards their 3D tile representations, and that permitted us to visualize both the knowledge graphs and ontologies representing these entities and their 3D representations without being limited by any technologies that were missing in the semantic web. I will note also that GeoSparkle, by the time we published this paper, GeoSparkle supported only 2D geometry. Since then, I believe they've worked towards integrating 3D data into their representations. But yeah, for the time being, we're only using GeoSparkle for representing geospatial semantics. Now, for time-dependent components, we based our approach off of time slices and 4D fluents. This is something that's used in the state-of-the-art, where instead of giving whatever your real-world entity is, defining its time-dependent components, like for example, when it existed in the real world, when this information is valid, instead of attaching that to the entity itself, you attach it to a time slice of that entity. And this is very similar to how the CityGML's versioning module represents time, where a different snapshot of the city might look different than a different snapshot of the city afterwards. And using this type of time slice approach, we can store these time-dependent components. Now, for validating this data, we recommend using Shackle for validating structure. We didn't do much research with Shackle, but there is an OGC testbed that looked at transforming OCL constraints, which are rules that you can write in UML, and transforming those to Shackle constraints. So that's something that is definitely used in the state of the art and should be implemented for validating structure. If not, we highly recommend using OOPS, the ontology pitfall scanner, for achieving fairness. It catches many, many different errors, or not necessarily errors, but things that you could implement to improve the quality of your data, to achieve high quality linked open data. Things like making sure your ontology is available, it's conformant to RDF. If you're missing metadata, it can help catch that. It's a very, very cool tool for that. And if not, for more complex data validation, we use inferencing on logical consistency. Do the rules in the data model logically hold true? And so for this, you can use tools like reasoners, and it's very easy to do this when transforming from UML to OWL in this way, because constraints in the UML model, such as relations, cardinality, those are transformed automatically towards constraints in OWL. Then for more complex data validation requirements, we propose using logical rules such as swirl. We have a publication under review currently that proposes an approach for how we can do this with our time-dependent components. This lets us write rules such as, if X is true, then Y should be true, and you can add this data to your existing data sets. And this will allow you to validate things such as, for example, if you're given an interval of time T1 and another T2, where the end of T1 coincides with the beginning of T2. Oh, I forgot that one. Then you know that these two intervals of time meet temporally. And using rules like this, you can build more complex rule sets that allow you to validate more complex questions like, how can we detect if two buildings in two consecutive versions of the same neighborhood have logically consistent temporal properties? And you can also, in theory, write rules like this that match CityGML's proposed abstract rule test suite. And so next, we had a couple of different experimentations with how we can not only visualize these ontologies, but how can we use the ontologies themselves to navigate 3D data, 3D urban data. So this was an experiment we did towards the end of my thesis, where we took versioned CityGML snapshots of a neighborhood of the Greater Lyon metropole, where 4 snapshots were available, and we were able to, using the versioning module, detect which buildings changed and how between these snapshots, and then visualize these ontologies. And not only can the visualization help you identify which buildings in these neighborhoods were combined, which were demolished, which were added, clicking on the nodes that represent this data also can navigate in the 3D scene. For example, clicking on a building can zoom in on the building or highlight it. Clicking on a node that represents a version of the city at a time X can update the 3D scene to what the city looked like at that time. And then one of my colleagues is working on a way to visualize all of these versions, timelines, or scenarios of urban evolution in 3D spaces, which becomes a little bit tricky because now you're trying to visualize 4-dimensional data in 3D. And there's a couple different propositions for visualizing not only the changes of individual objects, but entire districts of the city in 3D space using these versioning approaches. And so what's next for these proposals? Well, recently, about a month ago, we had an issue in our GitHub, and Nataliya responded to us asking about our representations of CityGML. And we realized that our 2 propositions weren't, first of all, 100% compliant. There is actually a more CityGML 3.0 compliant representation that doesn't use OWL time that is probably more interoperable for the community. And this is something that I'll let her discuss more in her presentation. And that's basically the next steps for what we'd like to see our work used for. How can we create something that's much more conformant and much more useful for the greater community? All right, so I think that's about all the time I have. So thank you very much for your attention. And I believe there will be time for questions later in the presentations. Thank you very much.
Thank you. Shall I continue the discussion of what we did? And I would like to show what we decided to, how we decided to improve the work of Diego and the team. And actually our aim is named CityRDF. It is not City Owl, and we decided not to put it very serious. So we decided to take the name CityRDF, which is good to see. And I would explain what we have done already into 3 steps. So first I show which technical highlights, what was the transition from Diego's work to what we have in CityRDF. And then I'll take care about the fairness principles and what kind of evaluation we did. And then at the end, I negotiate a bit on how CityRDF can address semantic interoperability, having examples in simple conversion from GML to RDF, and pass then the storyline to Arkadiusz, and he will show the BIM and GIS logical reasoning in one model. So let me describe the technical highlights of our work. We took the source from Diego's UGGraph project, and we rely much on the enterprise architect file, which is CityGML 3.0 conceptual model. And we also took the shape change conversion that converts EA file into XML. So we will have the data, initial data of a UML model we have in XML, and then we use and extend the workflow that Diego's team performed, and the result we got as a source is the set of ontologies that is placed here. And this was our starting point, and we decided to look at the files, how they look like, and if they can be improved. So when we look at the example code, we see several, we catched several points that are repeatable and can be make better. So for example, we see long property name of the kind name.
Nataliya, can I just interrupt?
Sorry.
There was a question. Are we seeing a presentation? I'm also having difficulty finding this. Are you sharing your screen successfully?
Yes, I am sharing, but it might be that some restrictions are performed. Sorry for that.
Do you need to do some magic?
Yeah, wait a moment.
Sorry.
No, sorry, Nataliya, because I was thinking that you was like a presenter.
Yeah, I just made you presenter, Nataliya.
Thank you. Oh, thank you.
Perhaps just quickly go back and review.
Sorry.
Now let's check if you see now my screen. Please check now. Oh, I see it. And you?
No, Nataliya, no.
Sorry. Once again. No. Let me share it once again. It's nice. You didn't miss a lot.
Yeah, we can say it now.
No. Perfect. Thank you.
Okay, good. So we have looked at example code, and we have some points to improve. First, we have long property names that are namespace, then class name, and then property names. And unfortunately, property names repeat in a package and across packages. The most famous parts was boundary, address, usage, value, function, and so on. Also, we are aware of a lot of ADE, so application domain extensions that were introduced in CityGML 3.0, and they are like a placeholders and dummy, and they are not to be defined within the conceptual model, and they are just left as a placeholder for possible practical extensions. We decided that keep them in CityRDF canonical ontologies is not necessary, and can be extended only in some practical situations. In other examples, we see that duplicate property names again for frequently used properties. And if you open the conceptual model, you will see a lot of usages, a lot of addresses, and so. And we decided to do some practical steps to enhance the presentation of UD graph project, and we did several steps to make it better. So our aim was to make CityRDF compact and more readable, still following Semantic Web best practices. To do so, we decided to remove all mentioning of ADE classes and properties as optional from the canonical model. We decided to deduplicate property names used more than once, and to use global property reuse instead. To do though, we create common namespace and keep all such properties with their stable parts there. And we, as much as possible, try to avoid long property names, and instead we use namespace property as a much comfortable and compact presentation. We use the same environment as UD Graph team, so Java, Python, shape change. We test the queries to do transformations with on.text GraphDB, and we use RDFlib to call queries in Python. What transformation we proposed? So we rely on UD Graph shape change conversion from enterprise architect file to XML. Then we take UD Graph shape change conversion from XML to RDF and extend it to have, first, we decided to have union stereotype conversion, which is available in shape change, but it wasn't used by the team of UD Graph, and we decided to make use of it. And we decided to make use of global scope attributes whenever possible. And if we can, in the shape change testbed, this rule is available as rule all prop global scope attributes. So these two rules enabled in shape change transformation did the job. We also extend a workflow to get all files, and as a result, we have a GitHub repository that keeps several versions of CityRDF. Why several versions? I will explain. But if you go there, you'll see that these are the files that are presented here. Although this is a result of our efforts, and you can see that the list of files is the same, but they are much shorter, compact, and more like practically usable. Sorry. No, I don't want to stop sharing. I would like to go. So let's look in depth details. I presented a workflow in the following list. So the first query was the query to remove the classes related to ADEs, application domain extensions. This is single query, it's pretty simple. And this reduces a lot the size of ontologies. We will take care of the next steps. Then we do global properties explications. We did qualifying queries to detect which properties are reused more than once, and we formulated the list of such properties in data type properties and object properties. And due to the rule that we used from shape change, the global scope attribute generation, we saw a lot of these rules, a lot of these properties, and several queries that did the job to global property explication. Next, a lot of queries was written to move from longer property names to shorter property names. The problems here was not only that we have to take care of all the actions and definitions. The problem was that in CityGML UML model, there are some like missed scores definitions, and first we had to detect which properties are missing because we didn't count. So for example, we have 10 at the beginning and we should have 10 at the end, but we saw less. And then we decided to check the model, and it happens that scores definitions were lost. So there is no scores definitions in the model. And I think it was because of UML, like typos or minor discrepancies. So it was a while to do this transformation smooth. And finally, we get the result that the ontology has proper naming. And the last issue we worked with was the issue how to define domain and range of properties. So the simplest way was to use a schema. A schema domain includes and schema range includes, which is in the default version, which is called CityRDF. But then we decided to do like variation of this situation and to have two more renditions of CityRDF. First one is called CityRDF strict, which restricts both domain and range with construction with oval union of. And then we decided that it's too strict because the application domain extensions should take care of this RDF as domain, but they cannot affect the ontology CityRDF. So they will have to use the relaxed semantics, and we decided to have the CityRDF optimal, which is in the center here. So we keep domain definitions for property as schema domain includes, but we restrict RDFS range to have the oval union of definitions, so we will be able to reason if we are ranging properly in proper list of classes. And this part, this action and this transformation couldn't be performed with pure Sparkle, and this is the only place where pure Python code was written to make the job. So initially the plan was to use only Sparkle, but it wasn't the case to reach the goal of having the strict and optimal semantics. So we will write code specifically here. And in summary, I would say that we have 22 ontologies, which is okay, because 21 is according to CityGML 3.0 conceptual model, and 22nd ontology is called common, which keeps global scope attributes declarations. I will now show how it looks like, because it might be interesting just to see what we are talking about. This is the ontology, common turtle, that is common models that supports the definitions of object and data type properties reusable across packages. So we see the class usage function, and we have defined these properties with their reusable part. Also, we defined geosparkle alignments for common properties like lot, number, multi-curve, and multi-surface that they should be the subproperties of geo has geometry, and boundary as well, defined as subproperty of geo has geometry. Now this will allow us to reason, because we want to reason over geometries as well, in CityRDF. What do we say about code lists? As you remember, in the conceptual model of CityGML, there are the definition of particular list of values that are modeled according to the standard 19150 by shape change conversion. It is modeled like SCOS concept scheme and SCOS concept, but we decided to separate ontology from the possible rendition of code lists, and now they are stored separately to avoid punning in all. And the ontology is tested to be consistent. It is tested with Palette and Hermit, and is openable, nicely openable, thanks to Diego, because he spent a lot of time to do it openable nicely in Protege 5.5 and higher versions. And this is how it looks in Protege now. So we have a list of classes. I quick show that we have these inferred classes, not defined, but inferred. So this is the result of reasoning. So we have classes, and each class is defined like standard owl class. And on the right, this is a picture illustrating how these code lists are modeled. They are modeled as subclasses of SCOS concepts. And the list is here just to ensure that all the code lists described in UML model are present here. Also, in the conceptual model, there were defined several data types, and we also took care about this, and we have these data types, and these are presented like owl one-off. So, for example, for condition of construction value, we have a list of values defined in data type in the enumeration in the UML, and these values are present for each UML enumeration. And on the right, we see how object and data properties are presented. So they are also shortened. You see there is no class name, only like local name of the property, which we this was our aim, to see these properties like as short as possible, and now it is completed. Next, when we get the files, we would like to analyze if they are fair. Thanks to Rob, the explanation of fairness was already presented, so I just analyzed the fairness according to the particular metrics. And we have, in total, we have 5 requests, 5 criteria implemented already that are marked in green. 5 are ongoing because there is no specific place and there is no specific URI to be placed to host the CityRDF ontology as such, but it is ongoing work. And 3 of criteria of fairness are partially implemented because this is dependent not only on our efforts, it's also dependent, for example, rich metadata. This is dependent on CityGML UML model and the definition of vocabularies that, so we cannot rely fully on what is in GML 3.2 in time and ISO 19152. So as soon as they are fair conformant, the CityRDF is also conformant. So, but we cannot like enforce them to do their files, their ontologies fair. So that's the idea. But well, it probably we will have 10 criteria out of 30 implemented. And I will start talking about the semantic interoperability that CityRDF can be used for. I will just show a simple example and start, and then pass the microphone to the other presenters, but we envisage that CityRDF is used as a target ontology to run various transformations from CityGML to RDF OWL. For example, it could be FME custom transformation, it could be XSparkle scripts, and it could be any other transformations just to have this canonical model at the end. So CityRDF as canonical model at the end. And also we can use CityRDF as a modern language for urban data. For example, with validation in shuttle shapes generated from CityRDF as well. And we envisage that CityRDF can be used in data profiling when we don't need to have the old power of CityRDF and all definitions available in CityRDF, but only parts of them will be enough to keep some data profiles, for example, within a court or within a check. And this is, for example, how the transformation looked like from CityGML to OWL. So we took the data from City of Ingolstadt, which provides open data in CityGML, and we converted with custom XSparkle script to a turtle. And here I just highlighted how it looks the initial values, so references from construction package, and how they are presented in the target file. So you see that the target namespace is common because all these properties are belonging to the common namespace, which are reusable, and the status, low reference, and high references are reused more than once, so they are put to common namespace. And I would like to stop sharing now, and I'm free to open the questions and to pass the microphone to other. Thanks. Now I have to pass the microphone to Carl, I guess, but help me to do him presenter.
Yeah, I think that he is presenter as well.
Okay.
So Carl, I think that you can share your screen. Thank you, Nataliya.
Well done.
Yes.
So there are a couple of questions. There are a couple of questions in the chat. Maybe Nataliya, you can have a quick look at those, and then we'll deal with them later.
Yeah, perfect.
I'm reading. I'm interested in seeing.
So why don't you have a look at those, and then when we get to the discussion at the end, you can respond.
Yeah, probably, yes. Okay, thanks.
Okay, you're seeing my screen now?
Yes.
Okay,
yeah,
good.
Perfect. Thank you.
Okay, so the very first thing I'd like to do is to thank Diego for his work and Diego for his support and the efforts in the CityGML SWIG and other work that I've been doing using the transformation of the CityGML conceptual model to a form that you can actually compute on. This is actually a theme that I've pushed for years, and Diego has been very helpful and very responsive. And at one point, about 5 years ago, I started to try to use shape change myself to go through the transformation from the Enterprise Architect UML to eventually OWL. And I learned how much work that was really going to be, and I was so happy when I realized that, oh, Diego is actually doing this full time, and I just have to wait for him to finish, and then I can use his results. And that's exactly what I've been doing. So I really do appreciate Diego's work and Diego's support of what I've been trying to do. Another thing, which is really just a comment, is, and other people in the webinar might have different opinions, but my feeling is that the CityGML conceptual model transformed to an ontology, but in either view is something that's grown over the years in a uneven fashion. So there is a huge amount of detail in one aspect, and there are inconsistencies and sort of development time interfaces between how one part of the representation works and the other. So this process where the conceptual model is extracted into a form that can be computed on is super helpful in terms of getting the underlying concepts clarified, unified, and made internally consistent. So I think that's great progress. So what I'm going to talk about mostly is a project that started in January of this year. It will finish at the end of the year. So a one-year project to build a radiance field modeling service prototype. This is led from the Metaverse Standards Forum, which is an interesting organization of about 2,600 members, mostly companies, and it represents a lot of different interests in modeling worlds, from clothing for avatars to privacy and security to what our group, the real to virtual integration group, works on, is the matching of information in different spaces, merging them or integrating them into a specific world. And I'm mostly interested in the real world, or at least the physical world that I experience. So that's the focus. And the work is building this radiance field modeling service, which is a box that has a representation of things in time and space. If you present it with an image, it will return the location and orientation of that image. If you present it with a location and orientation, it will respond with an image. Or if you send a sequence of poses, you'll get back a video. Or if you send a video, you'll get a sequence of poses. So GeoPose is an OGC standard, and that's something that's used in the both inputs and outputs of the modeling. So if you're familiar with neural radiance fields, which really was a application of methods used in artificial neural network to representing things in the world for 3D Gaussian representations and 3D Gaussian splatting, or ray tracing to do rendering. That's what we're talking about here. So I'm going to, so these okay. Following the following slides I'm going to go through, except for one or two of them, just quickly, so you'll have an understanding of this, the structure that we're building inside of the radiance field model. But at the end, then I have sort of the result of the experience of using the OWL representations that were available on the Software Heritage Archive that is my access to Diego's results, or Diego and the team's results. So the structure we're using is conceptually a restricted area of space and time. And typically, in terms of space, it's an area of perhaps 1,000 meters in diameter. It is variable amounts of time, and the time is really scaled by the speed of interaction between things that have a mind of their own and which move, which we call actors. And these move against a background, which we call a stage. And both the actors and the stage are segmented into semantic classes. And the semantic classes that we use are derived, thanks to Diego's work, according to the CityGML3 semantic model. So the stage, basically you can think of the stage as things that don't move. And one of the ways that we actually segment and recognize entities within the space is by whether motion is detected. So we call that velocimetric segmentation as opposed to semantic segmentation. This is a moving compact set of things that are producing color in an observed imaging sensor. The stage elements, segmented semantically, are nevertheless able to change over time, and they may offer the ability for other things to interact with them through affordances, and the actors are the things that do the interaction. So the stage elements can't on their own interact. The property of being able to interact is behavior, and behavior is mediated in most cases by affordances. So beyond the structures of CityGML itself, we're interested in the water property. And I'm just going to go through these. You have access to the slides to get more detail if it's of interest. And I'll talk a bit about the semantic type. So we only use some of the modules from CityGML3. And this is because we weren't smart enough to understand how to use the other ones, or at least we thought the cost of incorporating them would be not worth the effort. And the ones that are listed here are the ones that we actually we actually use. We do, so in the earlier, I think Nataliya was talking about not really using the ADE mechanism, and we chose to support the ADE mechanism, which in a way contaminates the model with these ADE hook all through the ontologies. So it's not beautiful, but we thought that was actually useful to retain. For Exchange, we're packaging this using the GLTF standard, graphics library transfer format, GLTF2. The reason for that is that it's widely used. It also means that visualization just works. It's not necessary for software to understand the parts of the GLTF. GLTF's expressed in JSON. It's not necessary for the visualizer to understand extensions that are ignored. And so this is my conclusion. So, and Rob touched on this at the beginning. One of the big challenges, or at least one of the things that consumes a lot of effort, is dealing with the expressiveness or neutrality of RDF and OWL. We actually translate into a restricted schema that fits with the object recognition that we use, and which is simplified in comparison to the full detail of CityGML3's conceptual model. Interestingly, many of the approaches we took, for example, pushing all the abstract classes down into concrete classes and pruning the tree were also used in CityJSON. So as I understand it, CityJSON was constructed by inspection as opposed to automated transformation. So I'll finish by saying again, thank you, Diego.
You're very welcome.
So I guess now will be my turn. And I'll talk a little bit more about interoperability, semantic interoperability, which is achieved in here in CityRDF with some other standards. And I repeat certain things about ontologies, which were already said, but I think it is not a bad thing actually to repeat because maybe there is a mixed audience and not everybody is very fluent with this yet. So I'll start with what is actually ontology in OWL, and this basically Ontology Web language, and that's what is the shorthand for it. So those ontologies are based on description logics, which is a family of logics in general, and they distinguish two knowledge components in general. There is a terminological component called T-box and assertional component called A box. This terminological component is sometimes called also axiomatical component, theory, and the assertional is called facts. So yeah, this theory, like in other in terms of CityRDF, will say something like, okay, that if in the model there is a room, there must be some kind of building which this room it belongs to, and there must be certain kinds of properties of this room. Not all of them have to be always asserted in this assertional part, but this axiomatical or phenomenological part kind of provides a framework or a schema. Sometimes it's called a schema, which basically gives you all the different kind of possibilities. Those different city objects and their elements can be arranged to be valid city models. So that's the theory, and after that comes practice in a way, that where people do actual modeling using this terminology and a set of different kinds of rules and restrictions on this terminology to form certain kind of sentences about those city objects. And the knowledge base, which is actually a combination, because it's not possible to have assertion without this terminology. And terminology may be okay, useful, but maybe interesting, but somebody has to use it for some kind of work to do modeling in the end. So that's what it's for. And the in CityRDF, T-box is result of the CityGML conceptual model transformation to OWL, which Diego and Nataliya already presented in more detail. And the concrete models describing actual city objects in CityRDF are those A boxes in this ontology. And actually, this what Rob also mentioned, that the conceptual model is expressed in UML, XML, and the CityRDF is OWL expressed in RDF, actually, because OWL also could be expressed in different ways. And to be compliant with the Semantic Web standards by W3C, it is expressed in RDF. And this possibility of transformation of one and the same model between different languages, it already shows basically the semantic interoperability. So this shows that standardization is crucial to achieve this semantic interoperability, at least at this theoretical model, this terminological model, because there are certain rules. There is a vocabulary, certain rules for how to arrange this vocabulary in both sets of languages. And based on this, it's possible to design transformation from one language to another language. But the underlying conceptual model stays the same. We're able to say exactly same things and model same city objects in both languages. So next part, what is the A box in here in the CityRDF, this assertional part, is also a set of statements, because all of the in ontology, every kind of state, every assertion is a statement consisting of subject, predicate, object, and their whole A box and T box is one big conjunction of those statements. It's an ending of them. And depending on the level of detail, those statements can say something like that. At least at this location, there is 3D geometry, and it is a building. And this is illustrated on this image. And if in more detailed in higher levels of detail, this basically can say at this location there are multiple 2D and 3D geometries which taken together are buildings with walls, roof, windows, and they also perform certain functions. So that's what is the A box. This is the concrete expression of the concrete model. It's no longer theory. We are starting to get to practice. So that's how this this practice can be used in building a city, for instance. For the start, we can basically start very simply. We choose, okay, go somewhere, choose this piece of land. Okay, it looks nice. There's a river, water sources, different kind of things, features, choose spatial features, which could be already described in GML. There's the standard also by OGC covering all this. And the ontology for this is provided by GeoSpark. So in GeoSpark ontology, you can describe all those geospatial features as a spatial feature with different kinds of subtypes of this. And after we chose this piece of land, nice. Somebody has to create the land use plan for this. So in Germany, in particular, there is this Explanung format, which is used for this. That's what we used in Accord. It looks like this. Okay, you have a piece of land divided by different sectors. They have certain kinds of functions in them and different properties on top of GML. But there are still GML with enhanced semantics for this too. It's no longer only geometry, but something which says that this geometry is designed for certain use of this land. And after that we get our building models. Then they can be also in different formats. And as long as they are spatial, there is some kind of spatial design in them. As long as there is some kind of something which we can call geometry in CityGML, and is transformable to the spatial design, we can already use it. There are different ways of transforming this. In Accord project, we used FME. It's an extract transform load tool from the IFC to get to the spatial design, plus additional semantics of the use of rooms inside this building. That's what was needed for our purpose. So, and this in this way, we show that there's concrete model interoperability already here. And so we are no longer talking about this transformation of terminology between different languages, but we're already getting into practice because it's kind of difficult to have building models in different formats, land use plan in different formats, and go kind of backwards and forwards and check in between them without, it takes quite a lot of time. So this semantic web technology, when land use standards are transformed into RDF, and the IFC model is also transformed to RDF, and both are topologically related using geosparkle terminology. We can say basically certain parts of the building are in certain parts of this land use plan. So this provides already a kind of certain interconnection in between them via those topological relations. So we use three different ontologies basically. One is transformation of the land use plan to RDF. Second one is geosparkle ontology, which provides the terminology for the topology relation, and the third one is the CityRDF. And all this is interconnected. We also don't need any ADEs here because of the nature of this of RDF, that it allows to interconnect different types, different models, as long as they are all in subject, predicate, object. You know? So they all form big graphs like this, and you can connect and disconnect them at will, depending on the purpose. Because of this, when we arrive at this this kind of model, combined of three different aspects of our city, which we're starting to build here, we can already do automated spatial reasoning about this. So we can basically start to assess all answer certain questions and assess truthfulness of all those statements. First, what can be done is that what also Diego talked about and Nataliya talked about evaluation by reasoners, so we can check for the consistency with axioms expressing terminological parts. So saying, okay, that we will not have something like something like floor, which is below ceiling in a room. That they will be inconsistent with the theory in a part. And in addition to this, it's possible to reason about the interconnected models and assess if that's one of the kind of assessments can be done if the building parts. Particular building parts are conformed with the planned land use. So an example of this is if certain percentage of commercial use does not exceed certain threshold in residential sector. That is because all those if-else different kinds of if-else statements expressing rules also could be logically expressed as basically conjunctions of statements, and you can give Sparkle certain set of statements and it will say true or false. Yeah, and it answers the question whether it meets the certain conditions in order to for the answer to the question to be true or false. And those are simple, and those are questions which we answered within this Accord project. So we checked whether the building design is contained with X plan, whether all parts of the building are contained with a permissible lot coverage, whether use of building rooms does not exceed 5% of residential use, whether use of all building rooms is at least 60% of office use, whether building floor space index does not exceed planned floor space index prescribed by this X plan, whether building is not higher than permitted by X plan, and whether the building is within heritage protection area, which is also quite important thing for certain reasons, and whether building does not cross building boundaries. Yeah, so whether it's correctly placed in our land use model. So, and the other things outside of Accord, which I done also before this project, using also CityGML converted to ontology, to our ontology, were basically large city models, and there were different kinds of reasoning which could be applied to those large city models. One of them is the logical reasoning. So you could also assess distances between different city objects and say, okay, certain parts of the city have better locations for solar panels, for instance. Using different integration, you can assess energy demands for those parts and things of this sort. And the other project which I worked on was also using knowledge graphs of Singapore, which is also pretty big city, with land parcels of this big city were modeled as generic city objects, and they had zoning information in there. So and we were able to apply graph algorithms to this community detection algorithm, and all that shown that those zones fall into kind of three main categories. That what is brown is the kind of dark brown is mainly mix of commercial and residential. The lighter brown or orange in here is more industrial, and the lightest yellow color is other types. And if you ever go to Singapore, you will be able to see that it's actually true. If you go to different parts of this in the center and the west, you will see more residential and commercial. On the western part, you will see basically some sort of factories, and whereas the yellow is more like wilderness and parks and things of similar use. So yeah, thank you very much. And if you have any questions, I will be very happy to answer after everybody else.
Thanks, Arkadiusz. There were a couple of questions in the chat, and we don't have very much time. Nataliya, were you able to answer Klaus's question?
Let me answer from the latest to the earliest. So the first question was to Kurt Jetlund, right? What the change was, a change not via IFC all. We did a custom X Sparkle script, which is much faster. So it is not FME, it is much faster, and it is like custom prepared for the data, because the data was in CityGML 2.0, because Xplan is for CityGML 2.0. And this script is available in the project, and I can share the screen to get you to show the idea how it looks like, if you want to.
Probably a bit short on time. That was like 3 minutes.
Yeah. Okay. And the question regarding I like the comment on ADE, to have ADE property in the common namespace, and it's a good idea to have it, like unifying property for ADE. And regarding the question of Klaus Nagel, the answer is that, as you remember, in OWL, properties are first-class citizens. So we don't need to attach them to the classes to allow them to exist. That is why we went the direction of, we just calculated how many times these low reference and high reference are used. And it was more than once. And that is why we defined not like common, then height point low reference. We just defined it as reusable property. And then in ranges and in domains, we can restrict that it could be height or room height. It could be, so we restrict the domain and we can restrict the range. But the idea was to make these object properties and data type properties as a first-class citizens. So to make use of OWL as such. So this was the idea.
Thanks. Are there any other burning questions before I summarize? Okay, well, feel free to send questions, of course, through email and other channels. But just to summarize, I think hopefully this has convinced people that there is direct utility in having a machine-readable model. In fact, we could probably say it's a necessity to have a machine-readable model to do some of these types of applications. And therefore, we collectively need to find a way to move forward. I think we've seen there's plenty of expertise and willingness to work in terms of the group. It's really now a question probably of the CityGML group making a decision to follow up on the proposal that Diego made about a year ago about this as a work item. One final comment is that we reference many other ontologies in this process. So we probably need to think not about publishing a standalone ontology, but actually understanding how we should publish families of ontologies and how they relate to each other, so that there is a more complete picture. I think that we currently have a situation where we publish standards to stand alone with not enough visibility of how they relate to other standards. And I think that's a bit of a barrier to uptake because it's a complicated task. So does anybody have any other final thoughts they wish to share?
I just want to say a small comment. So looking at the presentations from the others, it's really cool to see people reusing the original model that we proposed, and also Nataliya. I really do like your guys' approach to the small little nuances in modeling CityGML. You solved a lot of problems in representing the standard that we didn't have the time to do, and it's really cool to see that.
Okay, great,
but this cannot be possible without your first efforts. So Diego, credits go to you first.
Thank you.
Thank you.
Yeah, no, I think we have a vibrant community, and I think it's now up to us to trigger some activities to formalize this into a work plan. So hopefully we can keep talking and share experience and get the message and the testing out into wider communities. In particular, I'm really keen to talk to Carl to understand how we can leverage some of those metaverse activities to progress this, because the various activities, including Geosparkle inside OGC, have not been well connected to some of the other activities, because there hasn't been this wealth of experience on how to exploit these machine readable models. I think we can solve that now. Well, I'll maybe just hand over to Micah for any final wrap up. Okay, I think Micah may have run into another meeting already. Okay, well, thank you very, very much to all the presenters. And even though I've been immersed in this and the ontology world for many years, I still found this fascinating, and seeing the depth of experience. And thank you very much for your time. And please feel free to shower us with more comments and questions as we go forward. And hopefully we will see a follow-up in terms of some formalization of this activity. Okay. Thank you very much.
Thank you.
Thank you.
Okay,
Thank you.
Thank you.
Bye-bye.
Bye.